Good morning. Today, we are going to look at how to make the world a better place to live in. We are going to look about renewable energy and in particular why we need it and why I believe that a technology called artificial photosynthesis is the key to possibly the best form of renewable energy. Let me start by telling why we need artificial photosynthesis. This is a chart of a planet's population and is projected to continue growing over the next century. What's more, most of those new people will be in the nations you see here in orange and red. These are developing nations, places where the standard of living is currently rising rapidly, and so too is the demand for new energy. Now, that's particularly a problem because of where we get our energy right now. So, of our current energy, all of it comes from one of two sources, either from deep with the planet, things like radioactive elements, or from sunlight. Now, wait, you might be saying, we don't put sunlight in our car. We put petrol or diesel in a car. We don't cook food with sunlight. We cook food with fossil fuels. Materials like coal, oil, or gas. Now, those materials, those complicated materials that we are burning now, were once biological material that were once animals and plants, and they got to be complicated molecules by the process of photosynthesis. In essence, when you use fossil fuels, you are using stored bank of sunlight from long in the past, but we don't want to use that stored bank because it's finite. So instead, we need renewable energy sources. Some of these sources have been used by humans for centuries. Things like wind power, hydroelectric power. Some of these technologies are relatively new, things like solar photovoltaics or geothermal power. But all of these energy sources have their own challenges or drawbacks, and most of those drawbacks come from how we distribute those resources and how we capture that energy and then it get to people who need to use it. So this is the whole story that we need to stop using fossil fuels. Tomorrow, we try not to use fossil fuels because carbon dioxide is something which causes global warming. But now, how to stop using fossil fuels? Is there any methodology to stop it or is there any alternate? Let's find an answer to it. There's plenty of energy that is available with the sun. Everyone agrees to it. This is an image of the whole solar spectrum. There is a small portion of the UV light. Maximum intensity is in the visible region. But we don't know how to tap this energy. The Earth receives about 174 petawatts of incoming solar radiation. If we can tap around 10% of it, then nothing happens to the global energy. Now, the question is, how to tap this solar energy? The classical way or the traditional way of tapping the solar energy is of course photosynthesis. In the extreme right side, we have the photovoltaics or solar cells. The middle image shows the image of photocatalysis. Here we have a semiconductor of optical bandgap that suits with the wavelength of sunlight such that the light is allowed to fall on the semiconductor in the presence of water. Both the process of oxidation and reduction take place which results in the evolution of hydrogen and oxygen molecules. We will be discussing about this method in detail. Now, what are the hydrogen production technologies available to us? Traditional methods like steam, methane reforming, and partial oxidation thermal hydrogen production technology and thermochemical hydrogen production technology grades up the average global warming. The other methods which produces green hydrogen are electrolysis, electrochemical, photochemical, photoelectrochemical that is PEC, biological, biochemical or photobiological methods and other methods. Of these, PEC that is photoelectrochemical method of hydrogen production is one of the much awaited technology for tomorrow. And PEC is a promise for the future because it produces green hydrogen, which is an unleashing power of sustainable energy. So, this is the basis of artificial photosynthesis, which is known to many of us. So, what is it? Artificial photosynthesis converts solar energy into chemical energy in the form of chemical fuels such as hydrogen and oxygen. For this to achieve, we require 1.23 volt for water splitting reaction. Now, let's consider a reaction in which hydrogen combines with oxygen. But if we combine these two molecules, we get 285.8 kilojoule per mole. Of that, 237.2 kilojoule per mole can be derived as Gibbs energy. But the rest of the energy is wasted in the form of heat. That is 48.6 kilojoule per mole is wasted in the form of thermal energy. But now, if we consider the reverse reaction, that is, if we want to split water tomorrow, we have to supply 237.2 kilojoule per mole. But still, we don't be able to push hydrogen and oxygen apart because some energy we have wasted in the form of thermal energy. So we have to supply a total of 1.48 volt instead of 1.23 volt. So splitting of water on equation, that is on paper, it seems to be very simple, but in reality, it doesn't go the way we think. So still, there is a hope for us looking at the nature. So in classical photosynthesis, we have carbon dioxide and water giving us oxygen and glucose. This is done in the presence of sunlight with the help of a natural green pigment which is known as chloroplast. In artificial photosynthesis, analogy to this, the green leaf is replaced with the help of semiconductor. Now, the next question is, did we identify a suitable semiconductor that has the potential to replace the leaf? Now, suppose if we split water, we get hydrogen and oxygen, of which hydrogen can be now stored and used as a fuel for tomorrow, and the oxygen goes into the atmosphere. We don't have to worry of it. This is the energy diagram of PEC by Fujishima and Honda done earlier in the 1970s. So here we need to tap the sunlight. For that we need to have a suitable photoanode, that is a semiconductor which helps in charge separation. Anodic reaction generates electrons in the conduction band. These things will be transported into the cathodic side where the reduction reaction is taking place. So here we have two half-cell reactions which are actually separated in this case. If we look at the literature, now the combination titanium dioxide, zinc oxide, zinc sulfide, strontium titanate, all can be selected as catalyst. Now how do we do this? In the figure left, this is the ideal representation. Here the first combination listed undergoes both reduction and oxidation. The second combination undergoes reduction. The third combination undergoes only oxidation. The last combination undergoes neither oxidation nor reduction. Thus, the ideal combination is only the figure 1 for the oxygen evolution and hydrogen evolution. So titanium dioxide, zinc oxide, cadmium sulfide, strontium titanate can do, but even though there are various combinations in literature, everything cannot be done. The very reason for this is normally if we shine the sunlight on a semiconductor, then the excitation is a very spontaneous process. Now, When the light is irradiated, the electrons in the valence band gets excited into the conduction band in 10 raised to minus 15 seconds. Now, what we want is that the electrons in the conduction band should not react with the holes in the valence band, and this process is known as recombination. Our job is to prevent the recombination. If you look at the time scales of this, recombination is a highly dominant reaction. Recombination competes heavily with the hole which can undergo oxidation. Now our job is to separate recombination. So for that we need to have a wide band gap semiconductor. Now how does we prevent recombination? The recombination can be prevented by making the particle in nanoscales. So here the surface recombination can be prevented by doping. Also, volume recombination can be suppressed by preparing semiconductor in nanoscales. Also, there are basically four methods in order to prevent recombination, and this one of the first method is mechanism of metal ion doped titanium dioxide photocatalysis. We can prevent recombination by doping metal ion doped with titanium dioxide. Here the dopants will form mid-gap states, so this lowers the band gap. Dopant will also act as electron and hole traps, which reduces the surface recombination. In a similar way, non-metal doping can be done. Another mechanism is mechanism of dye with titanium dioxide. The dye should be selected in such a way that the conduction band of dye should be more negative than the conduction band of titanium dioxide. Then the electron will quickly transported to conduction band of titanium dioxide. Another example from literature is by taking a quantum dot structure of cadmium sulfide. So here we can see cadmium sulfide also have a band gap of 2.5 electron volt compared to 1.23 electron volt. Then why we cannot use cadmium sulfide directly is because the main problem with sulfide is that it undergoes photocorrosion. So the four available combinations to prevent recombination that we have discussed are put a metal doping, put a non-metal doping, replace it with a dye, or take a small band gap semiconductor. Now let's see how it's done practically. If you look at the left side, we have photocatalysis or photocatalytic water splitting. If you look on the right side, we have photoelectrochemical water splitting, that is PEC. In photocatalytic water splitting, it's a single particle catalysis where both the reactions are being done by the same particle. In photoelectrochemical water splitting, we separate the reactions. We have anodic reaction, we have cathodic reactions, an electrolyte, the charge transfer mechanism, and so on. In PEC, we have to worry about the charge carrier generation, the charge carrier separation, the charge carrier transportation, charge carrier transfer at the electrolyte interface. Also, we have to worry about generation of PEC voltage required for water decomposition. And basically, what are the requirements of photoelectrodes? In PEC, the ideal band gap is around 2 electron volt. Ideal combination as shown in the right hand side picture. If this is the semiconductor, then the semiconductor conduction band should be more negative with respect to hydrogen evolution level. At the same time, the semiconductor valence band should be more positive with respect to oxygen evolution level. That is, if you try to sandwich hydrogen-oxygen evolution reaction within the band edge position of the semiconductor. To say about the material durability, it must be stable in aqueous solution under illumination. Also, its oxides must be stable. These are some of the latest combinations from the literature. Cu2O is a promising for tomorrow. Now, what are the challenges that we face using a PEEC is it reduce of recombination of photogenerated charge carriers, suitable visible light absorption and stability in aqueous electrolyte. Now, What are the different semiconductors that can be used in PEC water splitting? You can use a photoanode. In photoanode, it is made up of N-type semiconductors. Electrons are majority charge carriers. Oxygen evolution reaction take place at the photoanode surface, whereas hydrogen evolution reaction at platinum electrode. The second type of semiconductor system in PEC is by making a photocathode. Here, the photocathode is made up of P-type semiconductors. In photocathode, holes are majority charge carriers. Hydrogen evolution take place at the photoanode surface, whereas oxygen evolution take place at the platinum electrode. Now, you can make both the electrodes as semiconductors. Here, both electrodes are made up of P and N-type semiconductors. The P-type semiconductor contains an excess of holes, whereas the N-type semiconductor contains an excess of electrons. When an N and P-type semiconductors are used together to form a junction, the electrons in the N-type semiconductor migrate into the P-type semiconductor, leaving positive holes on its own surface. Oxygen evolution reaction takes place at the photoanode, whereas hydrogen evolution reaction takes place at the photocathode. Now, another complex thing in PEC is suitable electrolyte combination. The movement we put the semiconductor in the electrolyte, then at the interface, the complex phenomena can take place. So we have two electrodes, the P-type cathodic and N-type for anodic. So if we keep this in an electrolyte, there will be an alignment of Fermi level. For this to happen, band bending has to take place. For the N-type semiconductor, the bending will be in the upward direction, and for the P-type semiconductor, the bending will be in the downward direction. Now, if we work for all these improvements based on three factors, that is light harvesting. This can be achieved by plasmonic light harvesting techniques that uses unique optical properties of metal nanoparticles to enhance the absorption of light by semiconductors. Metal nanoparticles can support localized surface plasmon resonances, that is LSPR, which are collective oscillations of free electrons in the metal. Now, the second primary step for solar fuel production is by charge separation and transfer process. And the third is catalytic reaction process. Among these processes, charge separation and transfer is a key energy dry and delivery step in determining the overall solar energy conversion efficiency. Now, how we can improve charge separation and transfer is by bulk semiconductor engineering, semiconductor surface engineering, interface properties of semiconductor with other materials such as other semiconductors, metals, and metal oxide catalyst or substrate, electrolyte properties. The fundamental approaches that we use in order to improve charge separation and transfer in semiconductor is it can be by doping, it can by metal plasmon structure control, co-catalyst loading, heterojunctions with different semiconductor. Of these, we will be discussing about co-catalyst loading and heterojunctions with different semiconductor in detail. Now, before going to that, let's understand about what is catalysis. Suppose if we want to reach home, there are two paths. One path is energy driven path, and the second path is there is a short path which makes the traveling easier. Of course, we will choose the second path. So, what is catalysis? Catalysis provides a new way to reach our destination while expending less energy. Now, to say about co-catalyst loading, co-catalysts are usually introduced to accelerate water splitting reactions. It produces active sites for the catalytic redox reactions on the surface, enhancing charge separation or transportation efficiency due to the formation of junction between co-catalysts and semiconductors. Co-catalyst loading also reduces the hour potential as well as activation energy by changing the reaction pathways. So, co-catalyst loading can help in reducing the over potential of water from 1.48 to a smaller value. Some of the examples for hydrogen evolution reaction co-catalysts are platinum and palladium, whereas ruthenium dioxide, iridium dioxide, and cobalt oxides are best co-catalysts for oxygen evolution reaction. Now, what are the drawbacks of using co-catalyst is that the amount of co-catalyst must be optimized because the co-catalyst may block the light from reaching the semiconductor and the resistance of the co-catalyst may increase the charge recombination rate. Now, how does co-catalyst helps in hydrogen production? It enhances light harvest, it provides active sites, it improves catalyst stability. Also, it boosts charge separation. Now, what are heterojunction systems? An heterojunction system consists of electron accepting semiconductor and hole accepting semiconductor. So here we use two different types of semiconductor. Of course, there will be an interface at the junction due to difference in the direction of electron or hole movement across the heterojunction. The existence of interface with varying charges may lead to formation of internal electric field at the heterojunction. So when holes move to the other electrode or the electron from that move to the first electrode, there will be an existence of interface with varying charges, and this produces an internal electric field at the heterojunction, which may induce separation of photogenerated electron-hole pairs in both the semiconductors and at the interface, resulting into reduce the electron-hole recombination. And the efficiency of heterojunction system for water splitting depends on the appropriate band gap, proper band edge alignment with each other, and high stability. To see about the benefits of using heterojunction is it enhances the efficiency of electron-hole separation. It increases the lifetime and interfacial charge transfer rate of the photogenerated charge carriers. Heterojunction also has a staggered band alignment and creates a built-in potential which facilitates charge separation at the interface. It broadens the range of visible light photoresponse. From literature, tungsten trioxide, bismuth sulfide heterojunction acts as a highly efficient photoanode for PEC water splitting. Here you can see tungsten trioxide has a band gap of 2.78 electron volt, whereas cadmium sulfide has a band gap of 1.35 electron volt. So, from the periodic table of elements, these 6 shaded elements are known as platinum elements: ruthenium, rhodium, palladium, osmium, iridium, and platinum. These platinum elements are considered as efficient catalysts for water splitting due to their operating potential, high electrical conductivity, and good chemical stability. However, these materials are very costly. As we all know, they are very rare in nature and are restricted from large-scale applications, which makes them less preferable. So we have to look for an alternative. All these shaded elements in combination can be provided as an alternate for platinum elements. Recently, inorganic structured metal oxides such as scheelite metal tungstates with the formula MWO4, that is metals like magnesium, calcium, strontium, barium, copper, manganese, zinc, cobalt, nickel, all shaded over here, have received much more attention for industrial and technological application due to their exceptional physico-chemical properties. Among them, strontium tungstate with sheath symmetry from literature has received greater attention for various electrochemical applications such as water splitting due to its attractive properties. So we can use the combination of all these elements in order to replace our platinum elements. So with this, we come to the conclusion. So photoelectrochemical water splitting, that is PEC water splitting, is a promising method for solar energy conversion that utilizes sunlight to split water into hydrogen and oxygen. This process, also known as artificial photosynthesis, offers a clean and sustainable pathway for producing hydrogen, a versatile energy carrier with potential applications in fuel cells, transportation, and energy storage, etc. So tomorrow we can dream a home like this. That is, every home can maybe a self-sufficient, maybe self-sufficient for fuel production and fueling of our engines. That's it. Thank you.